All right, well, so far we've just wrapped up talking about the normal distribution, things like standardized scores, z-scores, and how to figure out area under the curve and lots of those things. So we're going to move sort of forward and sort of seeing how that applies when you take multiple samples and how we can make some assumptions about comparing samples either to a fixed value or to one another based on what we know about the normal distribution. But instead of doing it in the normal way, where I just sort of talk about it and we sort of go over the concepts and things, I'm going to do it in a different way. So instead of just giving you a regular lecture, today, during this sampling distribution and hypothesis testing lecture, I'm going to try to sell you some drugs. Now, not like illicit drugs, not the quote-unquote fun drugs, street drugs, but some pharmaceuticals. Okay, say I'm working for a pharmaceutical company and I have a new drug over there that I'm trying to sell you. IQ Plus. I want doctors and patient stuff to buy into the fact this drug works. So I'm going to do some testing and I'm going to show you the results and try to convince you that you really should be taking IQ Plus. All right, so in the context of selling you drugs, we're going to discuss what a sampling distribution is, or what they are in general, and we'll talk about some of the processes of hypothesis testing and why we do these crazy things like the null hypotheses, what test statistics look like in the distributions, and then we'll make sure and tie it together to the normal distribution, and really sort of figure out how the normal distribution can apply here when trying to compare samples to one another. And then we'll talk about some other important concepts as well. Okay, so let's say, this is obviously hypothetical. I don't have a drug to sell you, but let's say I did. Let's pretend for a second that I am some kind of chemist, maybe like the Breaking Bad character that develops my own drug and I'm now trying to sell it out there. So let's say we wanted to create a pill that when you take it regularly like a vitamin, it can increase your intelligence, actually make you smarter. Sounds like something everyone would want. Seems like a fairly straightforward thing. If there was something you could take to make you smarter, seems like everybody would want to take it. But, of course, everyone was going to want some proof that it works. So let's say I do something really simple. I take a group of 25 participants, and they're given 30 milligrams of IQ Plus every day for 10 days. And then at the end of the 10 days, I have those 25 participants. They're given the Stanford-Binet intelligence test. Now, just so that we're clear and we know sort of what we're talking about. In general, the Stanford-Binet intelligence test is designed so that the average, the population average for the test is 100. Right? It's designed that way. Right? So everyone that takes it, there's an average IQ score of about 100. The standard deviation for the test is 15. That is the way that the test is designed. It is scaled to be that way. It has a mean of 100, standard deviation of 15. That's fairly typical for IQ tests. So keep that in mind. Okay, so mean of 100, standard deviation of 15. All right, so we got these 25 people. They're taking IQ Plus after 10 days. After 10 days of taking IQ Plus, these participants have an average score of 106. Right, so they're 6 units higher than average. So the big question here, in trying to convince you whether or not this drug works or doesn't work, is whether or not you believe that 6 unit increase is really large enough to conclude that IQ Plus was even effective. All right, so is this increase large enough to conclude that IQ Plus was effective in increasing participants' IQ? And it really should be participants. Anyway, but that's a big question. How do I convince you of this? Most people, when they see that the average was 106, knowing again that the mean is 100, standard deviation is 15, most people right away think, well, 106 is not even a standard deviation. I mean, we haven't really changed them a whole lot. It's not even half of the standard deviation. It doesn't seem like a very large increase, really. So most people are sort of unimpressed by the fact that the average is 106. And it's actually, it's a fairly simple reasoning there, right? So if again, if 100 is the average, moving people 6 units, like, well, they can probably just get there on their own. Maybe you just happen to find people who are just a little bit higher than average, and IQ plus really had no effect. So the question comes down to, is the difference between 106 and 100 large enough to lead us to conclude that is a real difference? I really should have put like real in, is it a real difference, right? Is it something that we can believe is a real concrete change in IQ? So that question can be asked in a couple different ways. Would we expect a similar kind of difference if we repeated this experiment? So if I did it again, had a different set of 25 people take the drug for 10 days, would I expect the same increase? Or is the difference due to something called sampling error? So there's two different things going on. Because you might be thinking, well, I don't really care if we do it again, we get a similar result. I want to know, is that 6 unit change meaningful? Is that a real difference? So there's two different questions. Is this something that is occurring by chance? So is the difference due to something called sampling error, meaning that as you take samples from a population, you expect them to sort of vary somewhat. Each sample is going to have, even though we expect the average to be 100, the average is likely to vary a little bit just due to something called sampling error. Sometimes some samples may be a little above the population average, sometimes they can be a little bit below. And then there's a different question, where is 106 like a meaningful size, right? And then that comes back to effect size that we'll get to later. So first, let's answer this question of whether or not 106 could just happen by accident. Because if it could happen by accident, by just random sampling error, then it doesn't seem very impressive. But let's see how likely it is to happen. So sampling error, aka, or also known as sampling variation, is really the normal variability that we would expect to find from one sample to another, or from one study to another. It's the random variability among observations or statistics that is just due to chance. What that looks like, if we were to think about it, is if I have some large population, right? So this is my population of people which I'm targeting, right? Okay. And I want to take samples, so this is going to have some mean, and we know that mean, at least for my IQ is about 100. Each time I go to take a random sample from this population, I'm going to get something, what I expect is that I'm going to get a sample that's going to have exactly the same mean, right? I'm going to have some mean that sort of reflects that mean. Right? I know it sounds sort of weird, but we're going to have a mean that's actually going to reflect the mean of the population. That's what we expect to happen. But sometimes, just randomly, we're going to get samples that are slightly higher. Sometimes we're going to get samples that are slightly lower. Okay? Just by chance. That's just going to happen. We expect that if we were to look over the range of all these, if we were to take all these different samples and take their averages, that those means, these means down here, should generally average out to be the population. That's sort of the nature of the mean. So when we talk about the mean being unbiased, sometimes it's going to overestimate, sometimes it's going to underestimate. But in the long run, we should expect it to average out to the population. And that's actually what makes the mean sort of useful, and why we tend to focus on it instead of the median or the mode or something. So this variation from sample to sample is what we're talking about. There is just a random variation that occurs from sample to sample as we're taking multiple samples from the same population. So what we expect, we know it's there. But we need to have some way to sort of figure, well, how much random variability do we expect? Like, how much would be normal if we take these samples from the population over and over again? And that's what we're sort of talking about here. How do we estimate this, and how do we use it to inform our decisions about the one sample that we have? So if we had the time and the sort of luxury and the access to a large population, we could, okay, so this says, how could we assess sampling error? All right, well, we could take many groups of size 25. And notice that the sample that we're targeting is 25 people, so we got to stick with that number for it really to be applicable. So if we take many, many groups, and when I say many, I mean like a very large number of samples just over and over again for the population, and take many of those samples, size 25, and we don't do anything to them. Don't give them IQ plus. Just to see what they look like all by themselves with no intervention. And we could go through and record the average IQ for each group and get an idea of how much really these things are going to vary. We can plot that distribution out, the distribution of these many large number of samples. We can plot out their means, and what we get is a distribution called a sampling distribution. So think about it. When we have a single sample, we call that a distribution. We call that a sample distribution. We call it one distribution. But as soon as we take multiple samples, now the term for that is a sampling distribution. And what's being distributed are not scores, right? So scores are distributed in a single distribution, where means, in this case, the means of each sample, are going to be distributing in a sampling distribution, typically called the sampling distribution of the mean, because you could have a sampling distribution of the mode or a sampling distribution of the standard deviation. You could do this for any statistic you want. We just typically don't do it for those others. We typically want to know what the mean distributes like across multiple samples. So usually when people are talking about a sampling distribution, more often than not, they're talking about a sampling distribution of the mean, which is what we're talking about here as well. So we could create this distribution and see, okay, well, what do samples look like? How, what do they normally sort of look like just from sample to sample? So the distribution of any statistic that's repeated, from repeated sampling over and over again from the same specified population is called a sampling distribution. So the possible results for this example I'll show on the next slide. And what it does is it shows the kinds of means we would expect to find when people don't take IQ+. When we've done nothing to them, how much will we expect them to change from one sample to the next? So what I did is I generated a population, just a large number of individual scores. I did this using SPSS, a computer program that you guys are using through Citrix for your lab. So I used some syntax and I generated just a large number of scores. And then I had to go back and pull 25 scores from the population, calculate the mean, put those scores back, and then do it again. And I did that many, 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 many times. I think I did it like 10,000 times, some ridiculously high number. And what we see is first, this is the distribution of the individual scores. Okay, so I just took and I tried to generate a distribution that was really, really close to what we'd expect for IQ, that has the mean of 100, standard deviation of 15. I did pretty good. So there's a mean here for these are 100,000 scores. All right, so 100,000 scores. This is like if you had a population that had 100,000 people in it. I just sort of simulated this. This is just a simulated population. So I had these 100,000 scores, and the mean is real close. It's 100.06, real close to 100, and standard deviation is 15.024. So I got really, really close to this idea of a mean of 100 and a standard deviation of 15 in the population. All right. So I have these 100,000 scores. Great. Here's the thing. If I already have the population, if I already know what the population looks like, it's actually much easier to figure some of this stuff out because the population is known. There's a lot of known information here. That rarely happens. It doesn't happen very often where we actually know all the information about the population, and we'll talk about what that means later. So when we talk in the next topic about a one sample Z statistic versus a one sample T statistic, it really gets to this idea of, okay, well, what if we don't know like what the standard deviation in the population is? What if we don't know that information? Because oftentimes we don't. So this is a nice easy case because we do know that information, and we can actually, I can simulate it. I can actually figure out what it looks like. But here's the main thing. So if I have these 100,000 people, or scores in this case, and I want to take a sample of 25 from it, we know we took our 25 and we got a 106. So we want to know, looking at the scores, 106 doesn't seem like it's that interesting. Like here's 100, right? If I'm looking at my finger here, here's 100. 106 is just barely away from 100. It seems that's why when we initially hear about this idea of of this drug moving the IQ 6 units up, it seems like, well, that's not very impressive, because even if you're not thinking about it in this way, 6 units doesn't seem very much, especially when we know that the standard deviation is 15. But the problem is we're comparing the wrong things. You're comparing the distribution of scores in the population like this. You're comparing your sample of size 25 to what we expect individual scores to do when distributed in the population. Well, so we're sort of comparing apples and oranges. So we need to figure out, well, what do sample size 25, how do they vary from sample to sample, so we know where our sample is and how it sort of compares to other samples. So that's what I'm doing. I'm going to take 10,000 samples size 25. All right, so I took 10,000 samples, and I computed the mean of each sample. So I took 25 people out, computed the mean, put them back, got another random sample of 25, put them back, and did that 10,000 times. And this generated a sampling distribution of the mean. So every individual value here is a mean of 25 people, 25 scores. And what you see is the mean ends up coming out pretty close to what we should expect. The average of all the averages, right? So we have means here. So the average of all the means, the mean of the means, is 100. It's real close, 99.96. So we had 100 was the mean of all the scores in the population. Well, the mean of all the means is right about the same. I mean, we're off in, like the second decimal place, right? So it's really close. But now look at the standard deviation. It's much smaller, right? So we went from having a standard deviation in the scores of 15, where the means are deviating in a much smaller way. That makes some sense. Getting individual scores to spread out seems pretty easy. One person, moving around. But to get 25 people to move up or down randomly, it's going to take a lot. It's going to be a lot harder. In order for a mean in a sample to get pulled up, you got to have a lot of some high scores or a lot of scores piling up on the right hand side to pull the whole mean up. Same thing for when it gets pulled down. So we'd expect that the means of samples wouldn't spread out, wouldn't deviate as far as they would for scores. All right, but how do we know by how much? Well, this is like a fifth the size. We went down from 15, a deviation of 15 in the population for the scores, so now we're only looking at a deviation of 3. Right, so the sample means are only deviating about 3 units instead of 15. So with these 10,000 samples, we're getting that the means only deviate at about a standard deviation of 3. So let's think about what that looks like. So in our minds, when we see the 106, and again, we're sort of unimpressed by the 106, it's because we're thinking about the distribution of scores, and we're thinking about, look, 106 is like barely right here. It's barely even moved the needle away from the mean, because the standard deviation is 15 units. So it's not even gone half a standard deviation. So it doesn't seem very impressive. But again, we're comparing it to the wrong thing. Our metric is looking at the scores of samples, the scores of the population. What we really need is to look at the means of samples taken from that population. Because when we do that, all of a sudden now that same change that looked so small before is now seems like way farther away. Our 6 units is now up here. So it's moved the needle quite farther when we compare it to the right thing. So as we take samples from the population, getting a sample to actually move 6 units above the mean is actually a lot more impressive, right? Because now we've gone 2 standard deviations away from the mean when we look at the standard deviation of sample means across multiple samples. Okay, so it's moved it 2 standard deviations. But is that really enough for us to even care? Is that really even, it doesn't seem like it's that impressive either. Like, all right, so big deal. 2 standard deviations. Is that really enough for me to believe that that it's really worked? Well, let's think about that. From what we know from the rough estimation chart, right? So we had that before, where we said, okay, there was like 34%. And 34% on either side of the mean, right? 34 and 34. And then it was 14. right? And then it was 14 here too, and then it was 2, and it was 2. Those are sort of the rough estimation piece. Those are all percentages. That's a horrible 14, 14, 14. Okay, so we know that up to here, right, if we look at just this part of the distribution, right, this is 50%, right? So to here, then to one standard deviation, we know that this whole thing is 84%. 84%. My 8 is a little goofy. 84%, like that. All right. So if I go to 2 standard deviations, I add another 14%. That's telling me that the percentage from here down to, you know, infinity, right, is 96%. 96%. That also tells me that going this way, right, based on this, I only have, I did that wrong, not 96. I can add, I swear, 84 plus 14 is not 96, but 98. 98% there, which means I only have 2% sort of above that number. So we're at 2 standard deviation means where our sample is, 106. So that means that there's 98% of other samples are less than our distribution. So we have 98% of samples are going to fall below it, and we're only going to get about 2% above. So to get a score, a mean of 106 or more, really there's only a 2% chance of getting 106 or above. So our 106 is falling at this very small percentage of scores, right? So we're talking about it's in a proportion of scores. It's only like, you know, 2% or so of the total total samples from this population. That seems rather unlikely, right? So what is this saying in general? You know, if we take samples from a population where the mean is 100 and the standard deviation is 15, and we take sample size 25, and we want to know, okay, well, how often would we get a mean of 106 just by chance, just because of sampling error, sampling variation? How often would we get a score of 106? Well, it looks like we're going to get a score of 106 about 2% of the time, less, 2% or so of the time. That seems rather rare, right? It seems fairly unlikely to get a score of 106. It's not impossible. You can get it. There's a chance that it can happen, but it's still a fairly rare event, something that's very, very unlikely. So the rationale comes, well, if 106 if this is unlikely, now I'm using the term unlikely sort of loosely because I haven't really even defined that yet, but 2%, I hope everyone would agree that 2% seems fairly unlikely. Unlikely to occur, unlikely to happen by chance. So if it's unlikely to happen by chance, what's a better explanation for why we're getting 106? If it isn't chance, if it's not random variability alone, well then why? Why would we get 106 in our sample if chance seems unlikely? Well, it's because better explanation is that IQ Plus worked. Right? So there's two options. IQ Plus worked and moved people up, or we got the score by chance. All right? Just randomly got to 106. If 106 by chance seems unlikely, it seems like, well, it's not very likely to happen by chance alone, then it makes it seem like IQ Plus is a better explanation. IQ Plus working actually seems to explain the outcome better than chance, because chance seems so unlikely. And that's really the basis of how we set up these kinds of problems to try to decide on whether or not something has worked or not, is to figure out, well, how likely is it to have occurred on its own? And if that's unlikely, then it's probably the thing we did, in this case, that we gave people IQ Plus, that actually moved their scores to an unusual place. 106 is pretty unlikely given our scenario here. So if 106 by itself is fairly unlikely, it's probably the IQ plus that we gave them. Now, again, I want to reiterate, it doesn't prove that it's IQ plus, right? We have not proved that IQ plus worked. We've just given evidence that it works. So it's now, we have at least one set of evidence that IQ plus was able to move scores to a place that seems unlikely to happen due to chance. So that seems like it's like a, 1 plus in the IQ plus column versus the random chance column, right? So we've now at least given some evidence to support the idea that IQ plus works. But that's just a start. We'd actually have to do it a few more times, see that we get some regularity in finding these kinds of means with IQ plus. But this is at least still, it's a start. And hopefully this has actually convinced you a little bit more that IQ plus is working compared to before, when you were thinking, all right, well, 106 versus a standard deviation of 15 doesn't seem very effective. All of a sudden now you start looking at means, you think, oh my, the standard deviation for means is only 3. And we've gotten 2 of those standard deviations away from the mean. That seems a lot more impressive than we were comparing it to 15 a second ago. So again, the logic here is that because it's unlikely to have happened by chance, we're going to use that as an argument to say that it's more likely, it's more feasible that IQ plus worked and moved the sample up 6 units than to get 6 units just by chance alone. So what do we conclude here? When people don't get IQ plus, right, the majority of the sample means fall between 94 and 96. And now again, this term majority, is fickle. Right? Because what we call the majority could be anything. So let's think about what that looks like, really. Okay, so the majority of sample means could be anything. We know that based on what we know about the normal distribution, from 97, which is 1 standard deviation below, and to 103, which is 1 standard deviation above, we'd expect this area to be 68%. Now that's already a majority. I mean, a majority is more than 50. So if I know that 68% is above, I could make the argument, well, since our sample is, in over here, right? So here's 106. Since our sample's over there, it's already outside of the majority. But people aren't comfortable with just a 68% or a 70% majority, so we go even further. We tend to define majority even more than that. We want to be a little more strict about what we mean about the majority. So if we go to another standard deviation, right, we know that this distance from here to here is 98%. Right? So 98%, because if we go to 106 on this side and 94 on this side, that's the 2 standard deviations, so that's 34 and 14, right, on one side. So 34 and 14 is 48. 48 and 48 is, oh wait, sorry, it's not 98, it's 96. Sorry, 96%. And we got the 2% there and 2% there, right? So we know that 96% of the distribution falls between 94 and 106. So here I'm just being a little bit lazy and saying, look, the majority in this case is, that we have 96% of scores fall between a mean of between 94 and 106. So we know that our 106 falls right at the very end of that. How do we generally define majority? Well, again, it gets tricky, and this is the thing that's been debated for a long time, and why we use this particular value and all this other stuff. So you've probably heard of having an alpha level equal to 0.05. Right? So this corresponds to 5%. Right? So 5% is how we typically define alpha, which I'll explain more in a second. What's more important for this idea is that the majority here is because we typically are thinking about the majority of scores. Where do the majorities of scores fall? Well, they fall in, the 95% of the distribution. So I'm using 96 here just because I'm being a little lazy, because I'm just going to a full negative 2 standard deviations on one side and a full 2 on the other side, which really gives us 96 and 4%. So 96 and 4 instead of 95 and 5. But 95 is typically how we define the majority. The majority of scores fall in the middle 95% in this case, or sometimes it can be the left or right 95%, depending on how you want to define it. But it comes down to, because we want to say, well, how do we define unusual? Remember I said it back in our last slide, that the reason why we can make an argument that our 106 really shows evidence for support for IQ Plus is because our 106 falls in a place that is very unlikely. And it's very unusual to get a 106 just by itself, just through random chance. Because getting it by chance is unusual, it's unexpected, has a low probability, we're going to decide in favor of IQ Plus instead of favoring on the side of random chance. So how do we define what is unlikely or unusual or rare or whatever? Well, we make that, forget what alpha is. We say that the majority of things are 95, because this idea is that we're defining 5% as what is sort of rare or unlikely due to chance. Okay, so we define 5%. So if something has a 5% or less chance, 0.05 probability or less chance of occurring due to random error alone, random sampling distribution alone, then sampling error is not a very good explanation. It's unlikely to have occurred by chance, so chance is not a very good explanation. And if chance isn't a good explanation, then whatever we did to the sample is a better explanation. So we tend to define rare or unlikely as something that is within this 5% region. So that's where this idea of alpha comes from. How do we define rare? How do we define unlikely? Well, somebody somewhere, I don't even know exactly how, because there's lots of different stories and different routes to how it came about, decided that 5% was the magic number, and it's been that way forever. We use alpha equals 0.05 as our magic decision process for what is rare and unlikely, and we've just stuck to it. And people have been criticizing it for a long time, but we were sort of stuck with that, and that's how it is. It's just a convention that has stuck around for a long time. So if we have decided that if our sample mean, if we do something to a sample of people, and the mean of that sample falls in a probability that is 5.05 or less, then that is where we decide, well, that means that chance is not a very good explanation, so what we did to them is a better explanation, and we've sort of stuck to that for a very long time. This is sort of the process, the thought process behind hypothesis testing and why we do it in this crazy way. Let's define what is unlikely. Let's figure out what unlikely looks like in a distribution of samples, and then figure out if our sample seems likely or unlikely. If it's likely, meaning it's close to or similar to the mean of the population, if it's likely, then we figure, okay, the sampling distribution, sampling error, sampling variation perfectly explains it, and we don't think anything of it. We figure, okay, people could get to 106 just by themselves without any problem. If it comes into the 5% region, we start thinking, well, has a 5% chance of happening on its own. That seems fairly unlikely. So IQ Plus is a better reason, a better explanation for how we got to that number. Now, for some of you that have seen this sort of process before, and you remember thinking about alpha levels being 0.05, and it becomes a sort of conventional thing. We sort of forget the reasoning behind it, but if you actually think about it, actually it's pretty smart. It's like it's a way of thinking about. We know that samples can vary from sample to sample, taken from the same population. So how do we know where really to draw a line that says that this is a meaningful result versus one that isn't very meaningful, and we could get it just from chance? And somebody had to make that decision, and 5% was it. Now, whether that was a good or bad decision depends, and you actually see some variation from field to field. In psychology, we're very much ingrained with this idea of 0.05, but you go into medicine and medical fields, they'll often do tests with alpha levels that are higher, like 0.10, 0.15, because they're trying to prevent certain types of errors over others. I'll come back to that in a second. So even though 5% is a sort of conventional thing that we typically use, it isn't always used, not by everyone, not all the time. So in thinking of sampling distributions, right, it's still a distribution, it's just now a distribution of means instead of scores. We still want to know, just like any distribution, we still want to know what's the central tendency look like, what's the average look like, and we want to know what the dispersion looks like or the variability looks like in the sample. So the central tendency of a sampling distribution is usually an estimate of the population parameter. Usually it's sort of funny. It's the mean of a sampling distribution is the mean of all the sample means. So the mean is the mean of the means. So remember, we took large population, we took little samples from it, a bunch of them, right, in our sample distribution of the mean. So if I took all these sample means, all these mean x's, and I summed all those up of each sample divided by the number of samples, right, that would give me a pretty good estimate of the population mean. That's what this is saying. The mean of all these means should be a pretty good estimate of the population mean. This is, I'm sorry, you can't see it really, but this is an n sub j, j being for each group. So if I take the mean, sum up all the means for all the groups, divide by all the number of groups we have, that's going to be a pretty good estimate of the population mean. That's what it means. That's why it says the mean, the mean, the means. So the central tendency of a sampling distribution tends to estimate fairly well the population parameter that you're trying to estimate, in this case the population mean. Okay. So what about the variability? Well, we know from our example that the variability of the sample means was much smaller, right? We went from a standard deviation of scores about 15 to a standard deviation of the means at about 3. So we know that there's actually a sort of a shrinking going on. It's actually going to be much smaller. So the variability, the standard deviation of a sampling distribution actually has a specific name. Even I was referring to up to that point as a standard deviation. It is technically like a standard deviation. It's taking it's the deviation of all these means around a central mean. So it is sort of like a standard deviation, but because they're means, we give it a different name. It's called a standard error instead. So remember, we're talking about sampling error, sampling variation. So if we want to have a measure of what that sampling error looks like, or the sampling variation looks like, well, that measure is the standard error, right? The size of that variation is the standard error, oftentimes called, referred to as SE. The shape of the distribution will depend on the statistic that you're trying to estimate. Like in this case, again, we're trying to estimate the mean, so that's going to affect things. And it's also going to be affected by a couple of assumptions. So the assumptions come down to something called the central limit theorem, as we'll come to in a second. But it's an interesting idea that the shape of a sampling distribution will depend on a couple of things: the number of subjects in the sample and the shape of the population. Okay, so there's really a couple different things that occur. I can show you an example of that using this link here, and you can play with it on your own if you like. Let's take a look at this link for 1 sec. You come to this thing, and it gives you some instructions. It says just click on begin, and you're given this. So this is an interesting breakdown where it shows you a population, and the population is normally distributed. So this first one's the parent population. And if I were to take a sample from here, in this case the sample is set to 5. The sample actually is set to a size 5. So it's going to take, in this window here, it's going to show you the individual sample data, and then it's going to calculate a mean for those samples. So if I animate that, what that does, it's randomly pulling out participants from the population. It's doing 5 of them, and it's giving me a mean. So here's the mean right here. I can do that again. Okay. So it's taking a random sample, calculating the mean, do it again. And it seems to be piling up pretty well right on top of itself. Alright, now I don't want to do this, you know, right now so far we've had 5 reps, 5 replications. So let's do it, we can do it 5 times. 5 times? 5, I can keep adding 5 reps over and over again. So it's doing that same process 5 times just in the background. But I can quickly just go, forget it, let's just do 10,000 of them. Let's do it real fast. There's 10,000. I can do 100,000. Do another 100,000. I can keep putting 100,000 there. As long as you get to a fairly large number, because the population is normally distributed, we expect this sampling distribution of means to be normal. It's just going to shrink. Right? This had a standard deviation of 5. Well, down here it's got a standard deviation of 2.24, so it's actually smaller. Right? So we know that the sampling distribution of the mean will be smaller, but as long as the population is normal, so will this. Okay. Now, what about if this isn't normal? So let's say it's skewed instead. So here's a skewed distribution. Now, since the population is skewed, if I keep a small sample, like a sample size 5, and I start to animate that, you know, most everything's going to fall down here. But every once in a while, you're going to get some extreme scores. Animate that again. So you're going to get some extreme scores that are going to pull the mean up. And even if I did this 10,000 times, you'll notice that this is the distribution of all the means. It still has a sort of fat right tail. It still looks fairly skewed, you know, a little bit skewed relative to this side. So if I have a parent population that is skewed, the sampling distribution of the mean will also be skewed if my n is small. If my n is about 5, it's gonna be a problem. What if I go to 10? All right, so let's do 10,000 size 10. Look, already at n size 10, meaning that each sample is about 10 people that I'm taking out of this population at a time. Like if I animate that, it's going to do 10 of those instead of 5. Now it's going to add the mean. So the tail here is still a little tiny bit skewed. It's not perfectly symmetric, but man, it's already getting pretty close. So what if instead I go to, let's go to 20. All right, if we go to 20, look at that. Maybe a little teensy tiny little tail on this side, but man, that looks fairly normally distributed relative to this. And of course, you know, the standard deviation was 6.22 up here, and it's down to 1.4, so it's definitely shrunk. But man, with n size 20, I've already got a fairly normal distribution. All right, that's pretty interesting. If I go to 25, right, perfectly symmetric. That tail is now gone. It's perfectly centered. So what about if I have some other shape? So what if my population is bimodal? Right? So I have some kind of bimodal distribution like this. Okay. Say, okay, bimodal. So what I would expect if I have a small samples like size 5, and I do this, I'm going to expect there to be sort of clusters around the 2 modes, these 2 peaks. And that's not going to be too surprising, right? You're going to get clusters around those peaks. So I do this 10,000 times. Look, it's already more normally distributed. Why? Because as you take samples from here and samples from there and you average them, you're going to get something right sort of in the middle. If I do this with n of 20, right, you're getting a normal distribution of means even though the population is bimodal. All right, if I do it with size 25, even more sort of normally distributed and skinnier. So we're getting a fairly normal distribution with even with the bimodal distribution up here. All right, so what's the takeaway from all this? There's 2 things that we can know or expect when we're taking samples from a population. And we're going to cover this again in the next slide. But as we saw in that example, if the population is normal, then we should expect a normal distribution of means regardless of the size. Even at size 5, an n size, you know, a sample size 5, the means distributed fairly normally. So if the population is normal, we would expect a normal sampling distribution. But when the population is not normal, what seemed to matter is the size of the samples. If we had small samples, the mean still distributed out in a sort of skewed way. It seemed to follow the skewness of the population. And when it was bimodal, it already was, even with a small number, it was still already fairly normally distributed, but it was sort of wide, had a lot of variability. But as we increased it up to 20 and 25, even when the population was skewed, the means distributed normally. Even when the population was bimodal, the means distributed normally. So we can get to a normally distributed sampling distribution in one of two ways, based on assumptions. If the population is normal, that sort of guarantees we'll have a normal distribution of means. Or if we have enough people in each sample. We have a large enough sample size. And different books, different sources will tell you a slightly different number. Sometimes it'll be 20 or more. If you have 20 or more, that's normal distribution. Sometimes you'll see it as high as 30. So somewhere in between there. So, 20, 25 people per sample, you're going to get a normally distributed sampling distribution of the mean, even if you don't know anything about the population it's coming from. But that's important because oftentimes we don't.